What if everything you thought you knew about the universe was just the tip of the iceberg? What if hidden forces, invisible to the naked eye, are shaping the very fabric of reality? From the mysterious pull of dark matter to the mind-bending possibilities of parallel universes, the cosmos is filled with secrets waiting to be uncovered. Today, we're diving into 30 of the most fascinating theories about the universe's hidden forces, ideas that challenge our understanding of space, time, and existence itself. Whether you're a seasoned space enthusiast or just curious about the mysteries beyond our planet, this journey will take you to the edge of what we know and beyond. So buckle up, because by the end of this video, you'll see the universe in a whole new light. Let's get started. Now, let's turn our attention to the first theory on our list, dark matter. Imagine looking up at the night sky and seeing only a fraction of what's actually out there. That's the reality we face when it comes to dark matter. It's a mysterious substance that doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, scientists are convinced it exists, and here's why. When astronomers study the way galaxies move, they notice something strange. The visible matter, stars, planets, and gas, doesn't account for all the gravitational forces at play. Galaxies spin faster than they should, and their outer regions don't behave as predicted by the laws of physics we know. This discrepancy led scientists to propose the existence of dark matter, an invisible form of matter that exerts gravitational pull but doesn't interact with light. Dark matter is thought to make up about 27% of the universe's total mass and energy. It acts like a cosmic scaffold, holding galaxies together and shaping the large-scale structure of the universe. Without it, galaxies would fly apart, and the universe as we know it wouldn't exist. But here's the catch: despite decades of research, we still don't know what dark matter is made of. It could be particles we haven't discovered yet, or something entirely beyond our current understanding. What we do know is that its gravitational effects are undeniable, and its presence is a cornerstone of modern cosmology. So, while dark matter remains invisible, its influence is everywhere, weaving the fabric of the cosmos in ways we're only beginning to comprehend. And as we move forward, this invisible force continues to challenge and inspire scientists to uncover the secrets it holds. Next up, we'll explore another hidden force that's equally mysterious: dark energy. What is it, and how is it shaping the fate of the universe? Let's find out. Now, let's shift our focus to another cosmic enigma: dark energy. If dark matter is the invisible glue holding galaxies together, dark energy is the mysterious force pushing the universe apart at an ever-increasing speed. It's a concept that challenges our understanding of the cosmos and raises profound questions about the ultimate fate of everything we know. The story of dark energy begins in the late 1990s when astronomers made a startling discovery. By observing distant supernovae, they found that the universe isn't just expanding, it's expanding faster and faster over time. This was completely unexpected. According to the laws of gravity, the expansion should be slowing down due to the pull of all the matter in the universe. But the opposite was happening, and scientists realized something extraordinary must be at work. That something is dark energy. It's thought to make up about 68% of the universe's total energy content, dwarfing even dark matter. Unlike gravity, which pulls things together, dark energy seems to act as a repulsive force, stretching the fabric of space itself. But what exactly is it? That's where things get tricky. One leading idea is that dark energy is a property of space itself, often referred to as the cosmological constant. This concept, first proposed by Albert Einstein, suggests that empty space isn't truly empty. It has an inherent energy that drives expansion. Another possibility is that dark energy is a dynamic field that changes over time, known as quintessence. But despite decades of research, we still don't have a definitive answer. the implications of dark energy are staggering. If it continues to dominate the universe, the expansion will accelerate indefinitely, leading to a future where galaxies are so far apart that the night sky will grow dark and empty. This scenario, known as the Big Freeze, is just one of the possible fates of the cosmos. Yet, for all its mystery, dark energy is a reminder of how much we still have to learn about the universe. It's a force that defies easy explanation, pushing the boundaries of our knowledge and inspiring scientists to explore new frontiers. As we move forward, let's turn our attention to another mind-bending concept: quantum entanglement. How do particles remain connected across vast distances, and what does it mean for the hidden forces shaping our reality? Let's dive in. Now, let's venture into the strange and fascinating world of quantum entanglement. Imagine two particles separated by vast distances, maybe even light years apart, yet somehow they remain deeply connected. What happens to one instantly affects the other, no matter how far apart they are. This bizarre phenomenon, known as quantum entanglement, is one of the most mind-bending concepts in physics, and it challenges everything we thought we knew about space, time, and the nature of reality itself. The story of quantum entanglement begins with Albert Einstein, who famously called it spooky action at a distance. He was deeply skeptical of the idea, as it seemed to violate the principle that nothing can travel faster than the speed of light. Yet, decades of experiments have confirmed that entanglement is real. When two particles become entangled, they share a connection that defies classical physics. Measure one and the other instantly knows the outcome, as if they're communicating faster than light. So, what does this mean for hidden forces in the universe? For one, entanglement suggests that there's a layer of reality we can't see, a hidden web of connections that operates beyond the limits of space and time. Some scientists believe this could be a clue to understanding how the universe works at its most fundamental level. It's as if the cosmos is stitched together by invisible threads, binding everything in ways we're only beginning to grasp. But entanglement doesn't just challenge our understanding of space and time. It also raises profound questions about the nature of reality itself. Could the universe be fundamentally interconnected in ways we can't perceive? Could entanglement be the key to unlocking new forces or dimensions that lie beyond our current knowledge? These are the kinds of questions that keep physicists up at night, and they're driving groundbreaking research into the quantum realm. One of the most exciting possibilities is that entanglement could play a role in the unification of physics. Right now, we have two major frameworks: quantum mechanics, which governs the tiny world of particles, and general relativity, which describes the large-scale structure of the universe. But these two theories don't play well together. Entanglement might hold the key to bridging that gap, offering a glimpse into a deeper, more unified understanding of the cosmos. As we peel back the layers of this quantum mystery, one thing becomes clear: the universe is far stranger and more interconnected than we ever imagined. And with every discovery, we're reminded that the hidden forces shaping our reality are as profound as they are elusive. Next, we'll explore another mind-expanding idea: the multiverse. Could there be parallel universes out there, each with its own set of hidden forces and cosmic rules? Let's find out. Now, let's take a leap into one of the most captivating ideas in modern physics: the multiverse. What if our universe isn't the only one out there? What if there are countless other universes, each with its own set of physical laws, hidden forces, and even alternate versions of reality? This is the essence of the multiverse theory, a concept that stretches the boundaries of our imagination and challenges our understanding of existence itself. The multiverse theory suggests that our universe might be just one of many, like a single bubble in a vast cosmic foam. These parallel universes could exist alongside ours, separated by dimensions we can't perceive. Some might be nearly identical to our own, with only slight differences, while others could be wildly different, governed by entirely unique laws of physics. The idea isn't just science fiction, it's a serious scientific hypothesis that emerges from theories like quantum mechanics, string theory, and cosmic inflation. So, how does the multiverse tie into hidden forces? Well, if there are other universes, they might be shaped by forces we've never encountered. Imagine a universe where gravity is stronger, or where electromagnetism behaves differently. These alternate realities could be governed by hidden forces that don't exist in our universe, or they might reveal new dimensions of reality that we've yet to discover. The multiverse theory opens the door to a cosmos far richer and more complex than we've ever imagined. One of the most intriguing aspects of the multiverse is the idea of alternate realities. Could there be a version of you living in a parallel universe, making different choices and experiencing a completely different life? While this might sound like the plot of a sci-fi movie, it's a question that some physicists take seriously. The multiverse theory suggests that every possible outcome of every event might exist somewhere in some universe. This idea not only challenges our understanding of reality, but also raises profound questions about free will, destiny, and the nature of existence. But how do we even begin to test such a mind-bending idea? While we can't directly observe other universes, scientists are looking for clues in our own. For example, cosmic inflation, the rapid expansion of the universe after the Big Bang, might have created bubbles of space-time that evolved into separate universes. Some researchers are also searching for evidence of collisions between our universe and others, which could leave faint imprints in the cosmic microwave background, the afterglow of the Big Bang. The multiverse theory doesn't just expand our view of the cosmos, it also deepens the mystery of hidden forces. If there are other universes, what unseen forces might be at work in them? Could these forces influence our own universe in ways we don't yet understand? These questions push the boundaries of science and philosophy, inviting us to rethink everything we thought we knew about the universe. As we ponder the possibilities of the multiverse, one thing is certain: the cosmos is far more vast and mysterious than we've ever imagined. And with every new discovery, we're reminded that the hidden forces shaping our reality might be just the tip of the iceberg. Next, we'll dive into another groundbreaking idea: string theory. Could the universe's fundamental building blocks be tiny vibrating strings? Let's explore this fascinating concept and its implications for hidden forces. Now let's shift our focus to a theory that reimagines the very fabric of reality: string theory. What if everything in the universe, from the tiniest particles to the vastness of space, is made up of something far more fundamental than atoms or quarks? What if the building blocks of existence are incredibly tiny, vibrating strings? This is the core idea behind string theory, a groundbreaking concept that seeks to unify all the forces of nature into a single, elegant framework. At its heart, string theory proposes that the fundamental particles we know, like electrons and quarks, aren't point-like dots, but rather tiny, one-dimensional strings. These strings vibrate at different frequencies, much like the strings of a musical instrument, and it's these vibrations that determine the properties of particles. A string vibrating one way might produce an electron, while another vibration could create a photon, the particle of light. This simple yet profound idea suggests that the diversity of the universe arises from the harmonies of these microscopic strings. But string theory doesn't stop there. One of its most ambitious goals is to unify all the fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces into a single, cohesive theory. For decades, scientists have struggled to reconcile gravity, which governs the large-scale structure of the universe, with quantum mechanics, which describes the behavior of particles at the smallest scales. String theory offers a potential solution by describing gravity and the other forces as different manifestations of the same underlying phenomenon, the vibrations of strings. To make this unification work, string theory requires extra dimensions beyond the three spatial dimensions and one time dimension we're familiar with. In fact, some versions of the theory suggest there could be as many as 10 or even 11 dimensions. These extra dimensions are thought to be curled up or hidden at such tiny scales that we can't perceive them directly. Yet they play a crucial role in shaping the behavior of strings and, by extension, the forces they produce. One of the most exciting implications of string theory is its potential to explain hidden forces. If the universe's fundamental building blocks are strings, then the forces we observe, like gravity and electromagnetism, might be the result of how these strings interact in higher dimensional space. This could open the door to discovering entirely new forces or dimensions that we've yet to detect. However, string theory isn't without its challenges. Because the strings are so incredibly small, far smaller than anything we can currently observe, testing the theory directly is extremely difficult. Scientists rely on mathematical models and indirect evidence to explore its predictions. Despite these hurdles, string theory remains one of the most promising candidates for a theory of everything, a single framework that could explain all the forces and particles in the universe. As we continue to explore the mysteries of string theory, one thing becomes clear: the universe is far more intricate and interconnected than we've ever imagined. The idea that everything from the stars in the sky to the atoms in our bodies might be woven together by the vibrations of tiny strings is both humbling and awe-inspiring. Next, we'll delve into another mind-bending concept, the holographic principle. Could our universe be a projection of information stored on a two-dimensional surface? Let's uncover the secrets of this fascinating idea and its implications for hidden forces. Now, let's take a step into a theory that challenges our very perception of reality, the holographic principle. Imagine if everything you see, touch, and experience in the three-dimensional world around you is actually a projection of information encoded on a two-dimensional surface. Sounds like science fiction, right? But this is the core idea behind the holographic principle, a concept that could revolutionize our understanding of the universe and its hidden forces. The holographic principle suggests that the universe operates like a hologram. In a traditional hologram, a three-dimensional image is created from a flat, two-dimensional surface. Similarly, this theory proposes that all the information about our three-dimensional universe, every star, planet, and even you, might be encoded on a two-dimensional boundary like the edge of the cosmos. This boundary could be thought of as a cosmic hard drive, storing the data needed to project the universe as we know it. But how does this connect to hidden forces? If the universe is a projection, then the forces we observe, gravity, electromagnetism, and the others, might not be fundamental at all. Instead, they could emerge from the way information is processed and projected from this two-dimensional surface. This idea flips our understanding of physics on its head, suggesting that the forces we've spent centuries studying might be secondary effects of a deeper, more fundamental process. One of the most intriguing implications of the holographic principle is its potential to resolve one of the biggest puzzles in physics: the black hole information paradox. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. According to classical physics, anything that falls into a black hole is lost forever, including information about its properties. But quantum mechanics tells us that information can never be destroyed. The holographic principle offers a solution by suggesting that the information swallowed by a black hole isn't lost, it's encoded on the black hole's two-dimensional surface, known as the event horizon. This principle also raises profound questions about the nature of reality. If the universe is a projection, does that mean our perception of three-dimensional space is an illusion? Could time and space themselves be emergent properties of a deeper, more fundamental layer of reality? These questions push the boundaries of our understanding and challenge us to rethink what we know about the cosmos. While the holographic principle is still a theoretical framework, it has gained significant traction among physicists. It provides a compelling way to reconcile quantum mechanics and gravity, two theories that have stubbornly resisted unification. By treating the universe as a hologram, scientists can explore new ways to understand the hidden forces that shape our reality. As we ponder the holographic principle, one thing becomes clear: the universe is far stranger and more interconnected than we've ever imagined. The idea that everything we see might be a projection from a two-dimensional surface is both mind-bending and awe-inspiring. Next, we'll explore another cornerstone of modern cosmology: the Big Bang and cosmic inflation. How did the universe begin, and what role might hidden forces have played in its explosive birth? Let's dive into the origins of everything. Now, let's journey back to the very beginning, the moment when everything we know came into existence. The Big Bang theory is one of the most widely accepted explanations for the origin of the universe, but it's not just about a massive explosion. It's about the birth of space, time, and the forces that govern them. According to the Big Bang theory, the universe began as an incredibly hot, dense point nearly 14 billion years ago. In a fraction of a second, it expanded rapidly, setting the stage for everything we see today. But here's where it gets even more fascinating. Scientists believe that this expansion wasn't just fast, it was exponentially faster than the speed of light. This phenomenon is known as cosmic inflation. Cosmic inflation suggests that in the first moments after the Big Bang, the universe underwent a brief but intense period of rapid expansion. This expansion smoothed out the early universe, making it remarkably uniform on large scales. It also explains why the universe looks the same in all directions, a concept known as isotropy. But what drove this incredible expansion? That's where hidden forces come into play. During inflation, a mysterious force, often referred to as the inflaton field, dominated the universe. This field is thought to have generated a repulsive force, pushing space apart at an astonishing rate. While we don't yet fully understand the nature of this field, its effects are etched into the fabric of the cosmos. For instance, tiny quantum fluctuations during inflation were stretched to cosmic scales, eventually becoming the seeds for galaxies and large-scale structures we observe today. But the story doesn't end there. Hidden forces may have also played a role in shaping the universe after inflation ended. As the inflaton field decayed, its energy was transferred to particles, creating the hot, dense soup of matter and radiation that filled the early universe. This transition marked the beginning of the universe as we know it, with gravity, electromagnetism, and the other fundamental forces taking over. One of the most compelling pieces of evidence for cosmic inflation comes from the cosmic microwave background, the afterglow of the Big Bang. This faint radiation, discovered in the 1960s, carries imprints of the early universe's conditions. Tiny temperature variations in the cosmic microwave background align with predictions made by inflation theory, providing strong support for this idea. Yet, despite its success, cosmic inflation raises profound questions. What triggered inflation in the first place? Was it a random quantum event, or was it guided by some deeper, hidden force? And what happened before the Big Bang? These questions push the boundaries of our understanding and remind us that the universe's origins are still shrouded in mystery. As we explore the Big Bang and cosmic inflation, we're reminded that the universe's hidden forces aren't just abstract concepts, they're the architects of reality itself. From the rapid expansion of space to the formation of galaxies, these forces have shaped the cosmos in ways we're only beginning to comprehend. Next, we'll turn our attention to another invisible force that gives particles their mass, the Higgs field. How does this field work, and why is it so crucial to our understanding of the universe? Let's uncover the secrets of the Higgs. Now, let's shift our focus to one of the most groundbreaking discoveries in modern physics, the Higgs field. This invisible force is the reason particles have mass, and without it, the universe as we know it simply wouldn't exist. But what exactly is the Higgs field and how does it work? Imagine the Higgs field as an invisible ocean that fills the entire universe. Just as a fish moves through water, particles move through this field. Some particles, like quarks and electrons, interact strongly with the Higgs field, which slows them down and gives them mass. Others, like photons, glide through without interacting, which is why they remain massless. This interaction is what gives everything in the universe its weight and structure. The existence of the Higgs field was first proposed in the 1960s by physicists Peter Higgs and others, but it took decades to confirm its existence. The breakthrough came in 2012 at the Large Hadron Collider, the world's most powerful particle accelerator. Scientists there observed the Higgs boson, a particle that acts as a signature of the Higgs field. This discovery was monumental. It not only confirmed a key piece of the standard model of particle physics, but also provided a deeper understanding of how the universe's hidden forces operate. But why is the Higgs field so important? Without it, particles would zip through the universe at the speed of light, never coming together to form atoms, molecules, or ultimately us. The Higgs field is the glue that holds the fabric of reality together, giving structure to everything from the tiniest particles to the largest galaxies. The discovery of the Higgs boson also opened up new questions. For instance, why does the Higgs field have the specific properties it does? Could there be more than one Higgs field? And how does this field interact with other hidden forces like dark energy or dark matter? These questions remind us that even as we uncover the secrets of the universe, there's always more to explore. As we reflect on the Higgs field, we're reminded of the intricate balance that makes our universe possible. It's a force so subtle yet so essential that its discovery has reshaped our understanding of reality itself. Next, we'll venture into the mysteries of the Great Attractor, a gravitational anomaly that's pulling galaxies toward it. What could be causing this cosmic tug of war, and what does it tell us about the hidden forces shaping the universe? Let's find out. Now, let's turn our attention to one of the most intriguing mysteries in the cosmos, the Great Attractor. This enigmatic gravitational anomaly, located in the direction of the constellations Centaurus and Hydra, exerts a powerful pull on our galaxy and thousands of others, drawing them toward it at incredible speeds. But what exactly is the Great Attractor, and why does it hold such sway over the universe? The Great Attractor was first discovered in the 1970s when astronomers noticed that galaxies, including our own Milky Way, were moving toward a specific region of space at speeds far greater than expected. This motion couldn't be explained by the visible matter in the universe alone, suggesting the presence of something massive and unseen. The Great Attractor lies about 250 million light-years away, hidden behind the plane of our galaxy, making it difficult to observe directly. This cosmic blind spot has only deepened the mystery surrounding it. So, what could the Great Attractor be? One leading theory suggests it's a massive concentration of dark matter, the invisible substance that makes up most of the universe's mass. Dark matter's gravitational pull could explain why galaxies are being drawn toward this region. Another possibility is that the Great Attractor is part of an even larger structure, such as a supercluster of galaxies whose combined gravity creates this immense pull. Some scientists even speculate that it could be a cosmic collision in progress, where multiple galaxy clusters are merging, creating a gravitational hotspot. But the Great Attractor isn't acting alone. Beyond it lies an even more massive structure known as the Shapley supercluster, which may be amplifying its gravitational influence. Together, these structures paint a picture of a universe shaped by hidden forces, where gravity weaves an intricate web that guides the motion of galaxies on a grand scale. The Great Attractor also raises questions about the balance of forces in the universe. How does its pull interact with the expansion driven by dark energy? Could there be other, even larger attractors out there, shaping the cosmos in ways we've yet to discover? These questions remind us that the universe is full of surprises, and the Great Attractor is just one piece of a much larger puzzle. As we ponder the mysteries of the Great Attractor, we're reminded of the unseen forces that govern the cosmos. It's a humbling reminder that even as we uncover the secrets of the universe, there's always more to explore. Next, we'll dive into the Fermi paradox, a question that has puzzled scientists for decades. If the universe is so vast, why haven't we found evidence of extraterrestrial life? Let's explore the possibilities. Now, shifting our gaze from the gravitational mysteries of the Great Attractor, we arrive at one of the most perplexing questions in science, the Fermi paradox. Named after physicist Enrico Fermi, this paradox asks a simple yet profound question. If the universe is so vast and filled with countless stars and planets, why haven't we found any evidence of extraterrestrial life? The universe is estimated to contain hundreds of billions of galaxies, each with hundreds of billions of stars. Many of these stars host planets in the so-called habitable zone, where conditions might support life as we know it. With such staggering numbers, it seems almost inevitable that intelligent civilizations should exist somewhere out there. Yet, despite decades of searching, we've found no definitive signs of alien life. This contradiction lies at the heart of the Fermi paradox. So, what could explain this silence? One possibility is that intelligent civilizations are incredibly rare. Perhaps the conditions necessary for life to evolve and reach a technological stage are so specific that they occur only once in a blue moon. Another theory suggests that advanced civilizations might self-destruct before they can make contact, whether through war, environmental collapse, or other catastrophic events. But what if the answer lies in hidden forces or phenomena we don't yet understand? Some scientists speculate that advanced civilizations might harness energy in ways that are invisible to us, making them undetectable by our current technology. Others propose that they could be hiding intentionally, avoiding contact with less advanced species like us. This idea, known as the zoo hypothesis, suggests that we might be living in a kind of cosmic preserve, observed but not interfered with. Another intriguing theory involves the concept of cosmic filters. These are hypothetical barriers that prevent civilizations from reaching a stage where they can communicate across the stars. These filters could occur at any point in a civilization's development, whether it's the emergence of life, the evolution of intelligence, or the ability to survive long enough to explore the cosmos. If these filters are common, it could explain why we haven't encountered other civilizations. The Fermi paradox also raises questions about the nature of the universe itself. Could hidden forces like dark energy or unknown physical laws be shaping the conditions for life in ways we don't yet comprehend? Or might there be civilizations so advanced that they've transcended the need for physical communication, existing in forms we can't even imagine? As we grapple with these questions, the Fermi paradox serves as a humbling reminder of how much we still have to learn about the cosmos. It challenges us to think beyond our current understanding and consider the possibility that the universe is far stranger and perhaps far quieter than we ever imagined. Next, we'll explore the simulation hypothesis, a theory that suggests our entire universe might be an artificial construct. Could hidden forces be part of the code running this cosmic simulation? Let's dive in. Now, let's take a step into one of the most mind-bending theories of all, the simulation hypothesis. Imagine for a moment that everything around us, from the stars in the sky to the ground beneath our feet, is part of an incredibly advanced computer simulation. This idea, once the stuff of science fiction, has gained serious traction among scientists and philosophers in recent years. But how could this theory explain the hidden forces shaping our universe? At its core, the simulation hypothesis suggests that our reality might not be the base layer of existence. Instead, it could be a highly sophisticated program created by an advanced civilization. Think of it like a video game, but on a cosmic scale. In this scenario, the laws of physics, the behavior of particles, and even the forces we can't directly observe, like dark energy or quantum entanglement, could all be part of the code running this simulation. These hidden forces might not be natural phenomena at all, but rather programmed rules designed to keep the simulation functioning smoothly. One of the key arguments for this theory comes from the rapid advancement of our own technology. If humanity can create virtual worlds with increasingly realistic physics and environments, it's not hard to imagine that a civilization far more advanced than ours could create a simulation indistinguishable from reality. In fact, some researchers argue that if such simulations are possible, the odds are high that we're living in one. After all, there could be countless simulated universes, but only one base reality. But how might hidden forces fit into this idea? If our universe is a simulation, then forces like gravity, electromagnetism, and even dark matter could be part of the underlying code. These forces might not be fundamental truths of nature, but rather carefully designed parameters to maintain the illusion of a consistent, functioning universe. For example, dark energy, which drives the accelerated expansion of the cosmos, could be a programmed feature to ensure the simulation doesn't collapse or run out of processing power. The simulation hypothesis also raises fascinating questions about the nature of consciousness and free will. If we're part of a simulation, are our thoughts and actions predetermined by the code? Or do we have some form of autonomy within the program? Some theorists suggest that glitches or anomalies in the simulation, like unexplained phenomena or strange quantum behaviors, could be clues that we're living in a constructed reality. These anomalies might be the equivalent of bugs in the code, hinting at the true nature of our existence. Of course, the simulation hypothesis is still just that, a hypothesis. There's no definitive proof that we're living in a simulation, but the idea challenges us to rethink our understanding of reality. It forces us to consider the possibility that the hidden forces shaping the universe might not be natural laws at all, but rather the work of an unimaginably advanced programmer. As we ponder this theory, it's worth asking, if our universe is a simulation, what does that mean for the future of science? Could we one day uncover the code behind reality itself? And if we do, what would that reveal about the creators of this cosmic program? These questions take us to the edge of what we know and perhaps beyond. Next, we'll explore the Casimir effect, a strange quantum phenomenon that might hold clues to the hidden forces at work in the fabric of space itself. Stay tuned. Now, let's shift our focus to a fascinating quantum phenomenon that might just hold the key to understanding some of the universe's hidden forces, the Casimir effect. Picture this: two uncharged metal plates placed incredibly close together in a vacuum. Despite having no charge, these plates are mysteriously drawn toward each other. This strange attraction is the Casimir effect, and it's one of the most intriguing examples of how the quantum world defies our everyday expectations. At its heart, the Casimir effect arises from the behavior of the quantum vacuum. Even in empty space, the vacuum isn't truly empty. Instead, it's teeming with virtual particles that pop in and out of existence in a chaotic dance dictated by the laws of quantum mechanics. These fleeting particles create fluctuations in the vacuum energy, and when two plates are placed extremely close together, the space between them restricts the types of fluctuations that can occur. Outside the plates, however, the vacuum energy remains unrestricted. This imbalance creates a pressure difference, pulling the plates together. What makes the Casimir effect so remarkable is that it demonstrates the tangible influence of quantum fluctuations, something that's usually invisible to us. It's a direct manifestation of the hidden forces at work in the quantum realm, forces that don't rely on traditional interactions like gravity or electromagnetism. Instead, they emerge from the bizarre and counterintuitive rules of quantum mechanics. But the implications of the Casimir effect go far beyond just two plates attracting each other. It offers a glimpse into the nature of vacuum energy, a concept that plays a crucial role in theories about the universe's hidden forces. For instance, vacuum energy is thought to be connected to dark energy, the mysterious force driving the accelerated expansion of the cosmos. If we can better understand the Casimir effect, we might uncover clues about how vacuum energy operates on a larger scale, potentially shedding light on one of the greatest mysteries in modern physics. The Casimir effect also challenges our understanding of space itself. It suggests that even the empty void of space is alive with energy and activity, hinting at a deeper layer of reality that we're only beginning to explore. This phenomenon has even sparked ideas about harnessing vacuum energy for practical applications, though such possibilities remain firmly in the realm of speculation for now. As we delve deeper into the quantum world, the Casimir effect serves as a powerful reminder of how much we still have to learn about the hidden forces shaping our universe. It's a phenomenon that bridges the gap between the microscopic and the cosmic, offering tantalizing hints about the true nature of reality. Next, we'll turn our attention to zero-point energy, the lowest possible energy state in a quantum system, and explore how it might connect to the universe's hidden forces. Stay with us as we continue to unravel the mysteries of the cosmos. Now, let's venture into the realm of zero-point energy, a concept that takes us even deeper into the quantum world and its hidden forces. Imagine a system where all motion has seemingly stopped, where temperatures have plummeted to absolute zero. Even in this state, something remarkable happens: energy persists. This is zero-point energy, the lowest possible energy state in a quantum system, and it's anything but empty. At its core, zero-point energy is the energy that remains when everything else is stripped away. It's the hum of the universe that never quiets, a fundamental property of quantum mechanics. Even in a vacuum where you'd expect nothingness, particles flicker in and out of existence, creating a constant buzz of activity. This energy isn't just a theoretical curiosity, it's a real, measurable phenomenon that underscores the strange and unpredictable nature of the quantum realm. What makes zero-point energy so intriguing is its potential connection to the universe's hidden forces. Some scientists believe that this energy could be linked to dark energy, the mysterious force driving the accelerated expansion of the cosmos. If zero-point energy exists everywhere, even in the void of space, it might contribute to the overall energy density of the universe, influencing its expansion in ways we're only beginning to understand. But the implications don't stop there. Zero-point energy has also sparked ideas about harnessing this seemingly limitless source of power. Imagine tapping into the energy of the vacuum itself, a concept that sounds like science fiction but is grounded in real physics. While the practical challenges are immense, the theoretical possibility has inspired researchers to explore how zero-point energy could one day revolutionize energy production. From advanced propulsion systems to new technologies, the potential applications are as vast as they are speculative. Of course, zero-point energy also raises profound questions about the nature of reality. If even the emptiest space is brimming with energy, what does that say about the fabric of the universe? It suggests that what we perceive as nothing is actually a seething sea of activity, a hidden layer of existence that defies our everyday understanding. This energy could be a key piece of the puzzle in our quest to uncover the universe's deepest secrets. As we continue to explore the quantum world, zero-point energy stands as a testament to the boundless mysteries that await us. It's a reminder that even in the stillness there's energy, a force that connects the smallest particles to the grandest cosmic structures. Next, we'll turn our attention to the quest for a theory of everything, a single framework that could unify all the fundamental forces of the universe. Stay with us as we delve into one of the most ambitious goals in modern physics. Now, shifting our focus to one of the most ambitious pursuits in science, we arrive at the theory of everything. This isn't just a lofty idea, it's the ultimate goal of physics, a single framework that could explain all the fundamental forces of the universe. Imagine a theory that ties together gravity, electromagnetism, and the strong and weak nuclear forces, weaving them into one elegant tapestry. It's the kind of breakthrough that could redefine our understanding of reality itself. At its heart, the theory of everything seeks to unify the two great pillars of modern physics: quantum mechanics, which governs the behavior of the smallest particles, and general relativity, which describes the large-scale structure of the cosmos. These two frameworks work brilliantly in their own domains, but they don't play well together. Reconciling them has been one of the biggest challenges in science, and it's where hidden forces might hold the key. Hidden forces like dark energy and dark matter could be the missing pieces in this grand puzzle. For instance, dark energy's role in accelerating the universe's expansion suggests there's more to gravity than Einstein's equations currently explain. Similarly, dark matter's gravitational effects hint at interactions beyond the standard model of particle physics. These mysteries might not just be anomalies, they could be clues pointing us toward a deeper, unified theory. String theory is one of the leading candidates in this quest. It proposes that the universe's fundamental building blocks aren't particles but tiny, vibrating strings. These strings could account for all known forces and particles, offering a way to merge quantum mechanics and general relativity. But string theory isn't without its challenges. It requires extra dimensions of space which we haven't observed, and it's yet to make testable predictions. Still, it's a tantalizing glimpse into what a theory of everything might look like. Another approach comes from loop quantum gravity, which suggests that space itself is made up of discrete loops. This theory aims to quantize gravity, bringing it into the quantum realm. While it's still in its early stages, it offers a fresh perspective on how hidden forces might fit into a unified framework. Both string theory and loop quantum gravity remind us that the path to a theory of everything is as much about imagination as it is about calculation. What's truly fascinating is how hidden forces might shape this ultimate theory. Could dark energy be a manifestation of quantum fluctuations in the vacuum of space? Might dark matter be evidence of particles we've yet to discover? These questions aren't just academic, they're central to understanding the universe's deepest workings. A theory of everything wouldn't just explain what we know, it would open doors to realms of physics we can't yet imagine. As we continue this journey, the theory of everything stands as a beacon of hope and curiosity. It's a reminder that science is never truly finished. There's always more to discover, more to unify, and more to understand. And who knows, the answers might be closer than we think, hidden in the forces that shape the cosmos. Next, we'll explore the black hole information paradox, a puzzle that challenges our understanding of what happens to information that falls into a black hole. Stay with us as we dive into one of the most perplexing mysteries in modern physics. Now, let's venture into one of the most mind-bending puzzles in modern physics, the black hole information paradox. This paradox strikes at the very heart of our understanding of black holes and the laws of physics. At its core, it asks a deceptively simple question: what happens to information when it falls into a black hole? According to quantum mechanics, information can never be destroyed. It's a fundamental rule. But black holes, with their immense gravitational pull, seem to defy this principle. So, where does the information go? To understand this paradox, let's start with what we know about black holes. When matter crosses a black hole's event horizon, it's gone forever, or so we thought. Stephen Hawking's groundbreaking work showed that black holes aren't entirely black. They emit radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate. But here's the catch: Hawking radiation appears to be random, carrying no information about the matter that fell in. If the black hole evaporates completely, where does the information about that matter go? This is the essence of the paradox. One theory attempting to resolve this mystery is the idea of black hole firewalls. Some physicists suggest that at the event horizon, there might be a fiery wall of energy that destroys anything falling in, effectively preserving information by encoding it in the radiation. But this idea is controversial because it contradicts Einstein's theory of general relativity, which predicts that crossing the event horizon should be uneventful, no firewalls, no drama. So, if firewalls exist, they'd require a radical rethink of our understanding of gravity. Another intriguing possibility is that information isn't lost at all, but is instead stored on the black hole's surface. This idea, known as the holographic principle, suggests that all the information about what falls into a black hole is encoded on its event horizon like a cosmic hard drive. When the black hole evaporates, this information could be released back into the universe through Hawking radiation. It's a fascinating concept, but it raises questions about how this encoding process works and whether it can truly preserve all the details of the original matter. Hidden forces might also play a role in resolving this paradox. For instance, some theories propose that quantum entanglement, the strange connection between particles across vast distances, could be the key. If particles falling into a black hole remain entangled with particles outside, perhaps the information is somehow preserved through these quantum links. This would mean that black holes aren't the information-destroying monsters we once thought, but rather complex systems that obey the rules of quantum mechanics. The black hole information paradox isn't just a theoretical curiosity, it's a profound challenge to our understanding of the universe. It forces us to confront the limits of our current theories and pushes us to explore new ideas about hidden forces, quantum mechanics, and the nature of reality itself. As we continue to probe this mystery, one thing is clear: the answers we find could reshape our understanding of the cosmos in ways we can't yet imagine. Next, we'll turn our attention to the cosmic microwave background, the faint afterglow of the Big Bang, and how it provides clues about the universe's hidden forces. Stay with us as we uncover more secrets of the cosmos. Now, let's shift our gaze to the oldest light in the universe, the cosmic microwave background. This faint glow, often referred to as the afterglow of the Big Bang, is like a cosmic time capsule, offering us a glimpse into the universe's infancy. Discovered by accident in the 1960s, this radiation has since become one of the most powerful tools for understanding the origins and evolution of our cosmos. The cosmic microwave background is essentially the leftover heat from the Big Bang, stretched and cooled over billions of years as the universe expanded. Today, it appears as a faint microwave signal that permeates all of space. But don't let its subtle presence fool you. This ancient light holds a treasure trove of information about the universe's hidden forces and its earliest moments. One of the most striking features of the cosmic microwave background is its near uniformity. No matter where we look in the sky, the temperature of this radiation is almost exactly the same, varying by just tiny fractions of a degree. This uniformity suggests that the early universe was incredibly smooth, but it also raises a question. How did such a smooth universe give rise to the complex structures we see today, like galaxies and galaxy clusters? The answer lies in tiny fluctuations, ripples in the fabric of space-time, that were present in the early universe. These ripples, imprinted in the cosmic microwave background, acted as seeds for the formation of everything we see around us. But what caused these ripples? Here's where hidden forces come into play. Many scientists believe that these fluctuations were generated by quantum processes in the first moments after the Big Bang, amplified by a rapid expansion of space known as cosmic inflation. This theory suggests that hidden forces, possibly tied to an unknown field or energy, drove the universe to expand exponentially in a fraction of a second. The cosmic microwave background provides crucial evidence for this idea, as its patterns match predictions made by inflation models. Beyond inflation, the cosmic microwave background also offers clues about the composition of the universe. By studying its temperature variations and polarization, scientists have been able to determine that ordinary matter, the stuff that makes up stars, planets, and us, makes up only about 5% of the universe. The rest is a mix of dark matter and dark energy, two of the most mysterious hidden forces in existence. Dark matter, which doesn't emit light but exerts gravitational pull, shaped the early universe's structure, while dark energy, responsible for the universe's accelerated expansion, continues to shape its fate. The cosmic microwave background is more than just a relic of the past. It's a window into the universe's deepest secrets. By decoding its patterns, we're not only learning about how the universe began, but also uncovering hints about the hidden forces that govern its evolution. As we continue to study this ancient light, we're reminded that the universe is full of mysteries waiting to be unraveled. Next, we'll explore the pioneer anomaly, an unexplained phenomenon that has puzzled scientists for decades and may hold clues about yet another hidden force in the cosmos. Stay tuned as we dive deeper into the unknown. Now, let's turn our attention to a mystery that has baffled scientists for decades: the pioneer anomaly. In the late 1970s and early 1980s, as the Pioneer 10 and Pioneer 11 spacecraft journeyed through the outer reaches of our solar system, something strange happened. Both spacecraft began to slow down slightly more than expected, as if an unseen force was gently tugging them back. This unexpected deceleration, known as the Pioneer Anomaly, became one of the most intriguing puzzles in space exploration. At first, scientists thought the anomaly might be due to something mundane, like a fuel leak or a technical glitch. But after ruling out these possibilities, the mystery only deepened. The deceleration was tiny, just a fraction of a millimeter per second squared, but it was consistent and couldn't be explained by known physics. This raised the tantalizing possibility that the Pioneer Anomaly might be evidence of a hidden force or even a new law of physics at work. One of the leading theories suggests that the anomaly could be linked to dark matter. If dark matter is distributed unevenly throughout the solar system, it might exert a subtle gravitational pull on the spacecraft, causing the observed deceleration. Another idea points to modified gravity, a concept that proposes our understanding of gravity might be incomplete, especially over vast distances. Some scientists have even speculated that the anomaly could be a sign of extra dimensions, where gravity behaves differently than in our familiar three-dimensional space. However, not all explanations involve hidden forces or new physics. Some researchers have proposed that the anomaly might be caused by something as simple as heat radiation. The spacecraft's nuclear power sources emit heat, and if this heat were radiated unevenly, it could create a tiny but measurable force pushing against the spacecraft's motion. This theory gained traction after detailed thermal modeling suggested it could account for much of the observed deceleration. Despite these explanations, the Pioneer Anomaly remains an open question. It serves as a reminder that even in the well-explored regions of our solar system, there are still mysteries waiting to be solved. Whether it's a hidden force, a new law of physics, or something else entirely, the anomaly challenges us to keep questioning and exploring the unknown. As we move forward, we'll delve into another fascinating concept: the idea of a fifth fundamental force. Could there be a force beyond gravity, electromagnetism, and the nuclear forces that we've yet to discover? Stay with us as we explore this intriguing possibility and what it might mean for our understanding of the universe. Now, let's shift our focus to a concept that could revolutionize our understanding of the universe: the possibility of a fifth fundamental force. For centuries, we've known about four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces govern everything from the orbits of planets to the binding of atoms. But what if there's a fifth force, one that's been hiding in plain sight, subtly influencing the cosmos in ways we've yet to fully grasp? The idea of a fifth force isn't just science fiction, it's a serious area of research in modern physics. Scientists have long suspected that our current understanding of the universe might be incomplete, and the search for this elusive force has led to some fascinating experiments. One of the most compelling pieces of evidence comes from anomalies observed in the behavior of subatomic particles. For instance, certain experiments with muons particles similar to electrons but heavier have shown slight deviations from what the standard model of physics predicts. These deviations hint at the presence of an unknown force or interaction. One leading theory suggests that this fifth force could be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. If dark energy interacts with matter in ways we don't yet understand, it might manifest as a new force. Another possibility is that the fifth force is tied to the existence of extra dimensions, a concept popularized by string theory. In higher dimensional space, forces might behave differently, potentially giving rise to effects we perceive as a fifth force in our three-dimensional world. To test these ideas, scientists are conducting groundbreaking experiments. For example, researchers are using particle accelerators to smash particles together at incredibly high speeds, searching for signs of new forces or particles. Other experiments involve ultra-precise measurements of gravity at microscopic scales, where a fifth force might reveal itself as a tiny deviation from the expected gravitational pull. Even space-based observatories are joining the hunt, looking for subtle effects that could point to the existence of this hidden force. While the search for a fifth force is still ongoing, the implications of its discovery would be profound. It could help explain some of the biggest mysteries in physics, from the nature of dark energy to the behavior of the universe on the largest scales. It might even bridge the gap between quantum mechanics and general relativity, two theories that currently don't quite fit together. As we continue to explore this intriguing possibility, one thing is clear: the universe still holds secrets that challenge our understanding. Whether the fifth force is real or not, the quest to uncover it pushes the boundaries of science and reminds us that there's always more to discover. Next, we'll dive into another fascinating concept, the anthropic principle, which explores why the universe seems so finely tuned for life. Stay with us as we unravel this cosmic mystery. Now, let's turn our attention to a concept that asks one of the most profound questions in science. Why does the universe seem so perfectly suited for life? This is where the anthropic principle comes into play. At its core, the anthropic principle suggests that the fundamental constants of the universe, things like the strength of gravity, the charge of an electron, or the rate of the universe's expansion, are finely tuned in a way that allows life to exist. If any of these constants were even slightly different, life as we know it might not be possible. But how does this fine-tuning happen? Some scientists argue that it's not a coincidence at all. Instead, they propose that hidden forces or deeper laws of physics might be at work, shaping the universe in a way that makes life inevitable. One intriguing idea is that the fine-tuning could be explained by the existence of a multiverse, a vast collection of parallel universes, each with its own set of physical constants. In this scenario, our universe is just one of countless others, and it's no surprise that we find ourselves in the one where the conditions are just right for life. After all, if the constants were different, we wouldn't be here to observe them. Another theory ties the anthropic principle to the concept of hidden forces or fields that influence the universe's structure. For example, some researchers speculate that a yet undiscovered force might subtly adjust the values of fundamental constants over time, ensuring that they remain within the narrow range needed for life. This idea is still speculative, but it opens up exciting possibilities for understanding why our universe is the way it is. The anthropic principle also raises philosophical questions. Is the universe fine-tuned for life by design, or is it simply the result of random chance? While science can't answer this definitively, it does provide tools to explore the possibilities. For instance, studying the cosmic microwave background, the afterglow of the Big Bang, can give us clues about the early universe and whether its conditions were inherently biased toward life. As we ponder these ideas, one thing becomes clear. The anthropic principle challenges us to think deeply about our place in the cosmos. It invites us to consider whether the universe's fine-tuning is a sign of something greater at work or simply a remarkable stroke of luck. Either way, it's a reminder of how much we still have to learn about the hidden forces that shape reality. Next, we'll explore another cosmic puzzle, the vacuum catastrophe, which highlights a surprising discrepancy in our understanding of the universe's energy. Stay tuned as we dive into this fascinating mystery. Now, let's shift our focus to a puzzling phenomenon that has left scientists scratching their heads: the vacuum catastrophe. This mystery revolves around a glaring discrepancy between what our theories predict about the energy of empty space and what we actually observe. According to quantum field theory, the vacuum of space isn't truly empty. Instead, it's teeming with virtual particles that pop in and out of existence, creating what's known as vacuum energy. The problem: when scientists calculate the expected amount of this energy, the result is staggeringly larger, around 120 orders of magnitude greater than what we observe in the universe. This enormous gap between prediction and reality is what's known as the vacuum catastrophe. So, what could explain this discrepancy? One possibility is that hidden forces or unknown laws of physics are at play, subtly balancing the vacuum energy to keep it within the narrow range we observe. Some researchers suggest that these forces might act as a kind of cosmic regulator, fine-tuning the vacuum energy to prevent it from overwhelming the universe. Others propose that our understanding of quantum mechanics is incomplete, and that new physics, perhaps even a theory of everything, could bridge the gap between prediction and observation. Another intriguing idea is that the vacuum catastrophe might be linked to the nature of spacetime itself. Could spacetime have properties we haven't yet discovered, properties that naturally limit the amount of vacuum energy? Or might there be a deeper connection between vacuum energy and dark energy, the mysterious force driving the universe's accelerated expansion? These questions remain unanswered, but they highlight just how much we still have to learn about the hidden forces shaping our cosmos. The vacuum catastrophe isn't just a theoretical curiosity, it has profound implications for our understanding of the universe. If we can solve this puzzle, it could lead to groundbreaking discoveries about the fundamental nature of reality. It might even help us uncover new forces or particles that have eluded detection so far. As we continue to explore this mystery, one thing is certain: the vacuum catastrophe reminds us that the universe is full of surprises, and that hidden forces may be at work in ways we're only beginning to imagine. Next, we'll delve into another fascinating theory, the ekpyrotic universe, which offers a bold new perspective on the origins of our cosmos. Stay with us as we uncover this intriguing idea. Now, let's venture into a theory that reimagines the very birth of our universe, the ekpyrotic universe. This bold idea suggests that the Big Bang wasn't the beginning of everything, but rather the result of a dramatic collision between two massive, higher-dimensional structures known as brains. Picture these brains as enormous sheets floating in a higher-dimensional space, occasionally coming into contact with one another. When they collide, the energy released could have sparked the expansion we now call the Big Bang. But what does this mean for hidden forces? Well, the ekpyrotic model proposes that the forces governing our universe might not be confined to the three dimensions we experience. Instead, they could extend into these higher dimensions, influencing everything from gravity to the behavior of particles in ways we can't yet fully comprehend. Some scientists speculate that hidden forces might mediate the interactions between brains, shaping the conditions that led to our universe's creation. This theory also offers a potential solution to some of cosmology's biggest puzzles, like the uniformity of the cosmic microwave background. In the ekpyrotic scenario, the collision between brains could have smoothed out irregularities, creating the remarkably even distribution of energy we observe today. It's a fascinating idea that challenges our understanding of space, time, and the forces that govern them. Of course, the ekpyrotic universe theory is still speculative, and much about it remains untested. But it opens up exciting possibilities for uncovering hidden forces that might operate beyond the limits of our current physics. Could these forces be the key to understanding the origins of our universe, or might they reveal entirely new dimensions of reality? As we continue to explore this theory, one thing is clear. The ekpyrotic universe reminds us that the cosmos is far stranger and more interconnected than we ever imagined. Next, we'll turn our attention to another mind-bending concept, the Boltzmann brain paradox, which questions the very nature of reality itself. Stay tuned as we dive into this intriguing mystery. Now, let's shift our focus to a theory that challenges the very foundation of our perception of reality, the Boltzmann brain paradox. Imagine this: in a universe governed by random fluctuations, why do we experience such a stable, ordered existence? This paradox arises from the idea that, statistically, random fluctuations in a chaotic system are far more likely to produce a single, isolated brain with false memories of a coherent universe than an entire, ordered cosmos. In other words, it's more probable for a brain to spontaneously form out of randomness, complete with fabricated memories of a structured world, than for the universe as we know it to exist. So, what does this mean for hidden forces? Some theorists suggest that hidden forces or mechanisms might be at play, ensuring that the universe remains stable and ordered rather than devolving into chaos. These forces could act as a kind of cosmic glue, maintaining the delicate balance that allows complex structures like galaxies, planets, and even conscious beings to exist. Others propose that consciousness itself might play a role in shaping reality, acting as a stabilizing force that prevents the universe from collapsing into randomness. The Boltzmann brain paradox also raises profound questions about the nature of existence. If our perception of reality is so fragile that it could be upended by random fluctuations, how can we trust our understanding of the universe? Some scientists argue that the paradox highlights the limitations of our current physical theories, suggesting that hidden forces or new laws of physics might be needed to explain why the universe appears so orderly. While the Boltzmann brain paradox remains a thought experiment rather than a proven theory, it forces us to confront the mysteries of existence in a way few other ideas do. Could hidden forces be the reason we perceive an ordered universe, or is consciousness itself a fundamental force shaping reality in ways we're only beginning to understand? As we ponder these questions, one thing is certain: the Boltzmann brain paradox reminds us that the nature of reality is far more mysterious and more interconnected than we often assume. Next, we'll explore another fascinating concept, the arrow of time, and how hidden forces might explain why time flows in only one direction. Stay with us as we unravel this cosmic mystery. Now, let's turn our attention to a concept that shapes every moment of our existence, the arrow of time. Unlike space, which we can move through in any direction, time seems to flow in only one way, from the past to the future. But why is this the case? What hidden forces or principles might be guiding this relentless forward march? At the heart of this mystery lies entropy, a measure of disorder in a system. According to the second law of thermodynamics, entropy in a closed system always increases over time. Think of it like a sandcastle on a beach. Left to itself, the sandcastle will crumble into a pile of sand, moving from order to disorder. This increase in entropy gives us a sense of direction in time, what we call the arrow of time. But could there be more to it than just entropy? some scientists speculate that hidden forces, perhaps even ones we haven't yet discovered, might be influencing the flow of time. For instance, could dark energy, the mysterious force driving the universe's expansion, also play a role in shaping how time progresses? Or might quantum mechanics, with its strange and unpredictable behaviors, hold clues to why time moves forward and not backward? Another intriguing idea is that the arrow of time might be tied to the Big Bang itself. At the moment of the universe's birth, everything was in a highly ordered state. As the universe expanded and cooled, entropy began to increase, setting the stage for the one-way flow of time we experience today. But what if there's more to this story? Could hidden forces have been at work during those early moments, ensuring that time would flow in a specific direction? The arrow of time also raises profound questions about our perception of reality. Why do we remember the past but not the future? Is it simply a consequence of entropy, or could consciousness itself be intertwined with the flow of time? Some theories suggest that our experience of time might be a result of how our brains process information, creating the illusion of a linear progression. While the arrow of time remains one of the most fundamental mysteries of the universe, it also offers a fascinating lens through which to explore hidden forces. Whether through entropy, quantum mechanics, or even consciousness, the flow of time challenges us to rethink our understanding of reality. As we continue to unravel this cosmic puzzle, one thing is clear: the arrow of time points us toward deeper questions about the nature of existence itself. Next, we'll dive into the quantum vacuum, the lowest energy state of space, and explore how hidden forces or fluctuations in this vacuum might shape the very fabric of the universe. Stay with us as we uncover more secrets of the cosmos. Now, let's shift our focus to the quantum vacuum, a concept that might sound like science fiction but is deeply rooted in the fabric of reality. The quantum vacuum is often described as the lowest energy state of space, but don't let the term vacuum fool you. It's far from empty. In fact, this so-called empty space is teeming with activity, a seething sea of particles and energy that pop in and out of existence in the blink of an eye. At the heart of this phenomenon are quantum fluctuations, tiny, unpredictable changes in energy that occur even in the absence of matter. These fluctuations are a fundamental aspect of quantum mechanics, and they hint at the presence of hidden forces that might be shaping the universe in ways we're only beginning to understand. Imagine the quantum vacuum as a calm ocean surface. From a distance, it appears still, but up close, you'd see ripples and waves constantly forming and disappearing. These ripples are the quantum fluctuations, and they might hold the key to some of the universe's deepest mysteries. One of the most fascinating ideas is that these fluctuations could be responsible for the very structure of the cosmos. Some scientists believe that the seeds of galaxies, stars, and even entire cosmic webs were planted by tiny irregularities in the quantum vacuum during the early moments of the universe. These irregularities, amplified by the rapid expansion of the universe during cosmic inflation, could have set the stage for the large-scale structures we see today. But the quantum vacuum doesn't just influence the past, it might also shape the future. Some theories suggest that the vacuum's energy could be harnessed, offering a potential source of limitless power. This concept, known as zero-point energy, is still in the realm of speculation, but it highlights the incredible potential hidden within what we once thought of as nothingness. Another intriguing possibility is that the quantum vacuum could be connected to dark energy, the mysterious force driving the universe's accelerated expansion. Could the vacuum's fluctuations be fueling this expansion, or even interacting with dark energy in ways we haven't yet discovered? The answers to these questions could reshape our understanding of the cosmos. As we explore the quantum vacuum, we're reminded that even the emptiest corners of the universe are filled with potential. From the birth of galaxies to the fate of the cosmos, the quantum vacuum might be one of the most powerful hidden forces in existence. And as we continue to probe its secrets, we're uncovering new layers of complexity that challenge our understanding of reality itself. Next, we'll take a closer look at the cosmic web, the vast network of galaxies and dark matter that spans the universe, and explore how hidden forces like gravity and dark energy shape this intricate structure. Stay with us as we journey deeper into the mysteries of the cosmos. Now, let's turn our attention to the cosmic web, a breathtaking structure that stretches across the universe like an intricate tapestry. This vast network, made up of galaxies, galaxy clusters, and dark matter, is one of the most awe-inspiring features of the cosmos. But what exactly is the cosmic web, and how do hidden forces like gravity and dark energy shape its formation? Picture the universe as a spider's web, with galaxies strung along delicate threads of matter connected by vast, empty voids. These threads, known as filaments, are the backbone of the cosmic web, and they're held together by the invisible hand of gravity. Gravity pulls matter together, creating dense regions where galaxies form, while leaving other areas nearly empty. But gravity isn't the only force at work here. Dark energy, the mysterious force driving the universe's accelerated expansion, also plays a crucial role. As dark energy pushes the universe apart, it stretches the cosmic web, creating even larger voids between the filaments. This interplay between gravity and dark energy shapes the web's structure, determining where galaxies cluster and how they evolve over time. Without these hidden forces, the cosmic web as we know it wouldn't exist. One of the most fascinating aspects of the cosmic web is how it reveals the universe's history. By studying the distribution of galaxies and dark matter, scientists can trace the web's evolution back to the early universe. Tiny fluctuations in the density of matter, amplified by gravity, grew into the filaments and voids we see today. These fluctuations, which originated in the quantum vacuum we discussed earlier, are the seeds from which the cosmic web grew. But the cosmic web isn't just a relic of the past, it's also a dynamic structure that continues to evolve. Galaxies move along the filaments, drawn together by gravity, while dark energy stretches the web on larger scales. This ongoing dance between attraction and expansion shapes the universe's future, influencing how galaxies will cluster and how the web will change over billions of years. The cosmic web is a testament to the power of hidden forces in shaping the universe. From the smallest quantum fluctuations to the largest structures in the cosmos, these forces work together to create the intricate, interconnected universe we observe today. As we continue to map the cosmic web, we're uncovering new insights into the nature of gravity, dark energy, and the universe itself. Next, we'll delve into the black hole firewall paradox, a mind-bending concept that challenges our understanding of black holes and the laws of physics. Stay with us as we explore this fascinating mystery and its implications for hidden forces in the cosmos. Now, let's shift our focus to one of the most perplexing mysteries in modern physics, the black hole firewall paradox. Imagine approaching the edge of a black hole where the pull of gravity becomes so intense that not even light can escape. This boundary, known as the event horizon, has long been thought of as a smooth, uneventful transition into the black hole's interior. But what if this isn't the case? What if, instead of a quiet threshold, there's a blazing wall of fire waiting to incinerate anything that crosses it? This startling idea is at the heart of the black hole firewall paradox. The paradox arises from a clash between two fundamental theories: Einstein's general relativity, which describes gravity and the smooth nature of space-time, and quantum mechanics, which governs the behavior of particles at the smallest scales. According to quantum mechanics, information about particles that fall into a black hole can't simply disappear. It must be preserved in some form. But if this information is somehow encoded at the event horizon, it could create a fiery barrier, contradicting the smooth space-time predicted by general relativity. So, how do scientists reconcile these two conflicting ideas? one possibility is that our understanding of quantum mechanics or gravity is incomplete. Some researchers propose that hidden forces or new laws of physics might resolve the paradox. For instance, certain theories suggest that the event horizon could be a region of extreme quantum activity, where particles interact in ways we don't yet fully understand. Others speculate that the firewall might not exist at all, and that the paradox is a sign that we need to rethink how information is preserved in black holes. The black hole firewall paradox isn't just a theoretical puzzle, it has profound implications for our understanding of the universe. If firewalls exist, they could fundamentally change how we think about black holes and the nature of space-time itself. On the other hand, if they don't, we might need to develop entirely new frameworks to explain how gravity and quantum mechanics work together. As we continue to explore this paradox, we're reminded of how much we still have to learn about the hidden forces shaping the cosmos. The black hole firewall paradox challenges us to push the boundaries of our knowledge, offering a glimpse into the strange and mysterious world where the very fabric of reality is put to the test. Next, we'll uncover the neutrino anomaly, a puzzling phenomenon that hints at the possibility of new physics beyond our current understanding. Stay tuned as we dive into this intriguing mystery and its connection to the universe's hidden forces. Now, let's turn our attention to another fascinating puzzle in the realm of physics, the neutrino anomaly. Neutrinos, often called ghost particles, are among the most elusive and mysterious particles in the universe. They're incredibly tiny, nearly massless, and rarely interact with matter, making them incredibly difficult to detect. Yet, despite their ghostly nature, neutrinos have been at the center of some of the most surprising discoveries in modern science. The neutrino anomaly refers to the unexpected behavior of neutrinos observed in various experiments. For instance, scientists have found that neutrinos seem to change their flavor as they travel through space. This phenomenon, known as neutrino oscillation, suggests that neutrinos have mass, a discovery that contradicted earlier assumptions and earned the researchers behind it a Nobel Prize. But that's not the only mystery. In some experiments, neutrinos appear to behave in ways that don't align with the predictions of the standard model of particle physics, the framework that describes the fundamental particles and forces of the universe. So, what could be causing these anomalies? One possibility is that hidden forces or new physics are at play. Some theories propose the existence of sterile neutrinos, a hypothetical type of neutrino that doesn't interact with matter at all except through gravity. These sterile neutrinos could explain the unusual behavior observed in experiments, potentially opening the door to a deeper understanding of the universe's hidden forces. Another intriguing idea is that neutrinos might be interacting with dark matter, the invisible substance that makes up a significant portion of the universe's mass. If neutrinos are influenced by dark matter, it could provide clues about the nature of both particles and the forces that govern them. Alternatively, the anomalies might hint at entirely new particles or interactions that lie beyond our current understanding of physics. The neutrino anomaly isn't just a scientific curiosity, it's a window into the unknown. By studying these ghostly particles, researchers hope to uncover new insights into the fundamental forces that shape the cosmos. Whether it's sterile neutrinos, dark matter interactions, or something entirely unexpected, the neutrino anomaly reminds us that the universe is full of surprises waiting to be discovered. As we move forward, we'll explore another cosmic mystery, the baryon asymmetry problem, which delves into why matter dominates over antimatter in the universe. Stay with us as we unravel this profound question and its connection to the hidden forces that govern our reality. Now, shifting our focus to another profound cosmic mystery, we arrive at the baryon asymmetry problem. This puzzle lies at the heart of one of the universe's most fundamental questions. Why does matter dominate over antimatter? According to our current understanding of physics, the Big Bang should have produced equal amounts of matter and antimatter. Yet, when we look around, we see a universe filled with stars, galaxies, and planets, all made of matter. So, where did all the antimatter go? The Baryon asymmetry problem challenges us to explain this imbalance. If matter and antimatter had been created in equal amounts, they should have annihilated each other, leaving behind a universe filled with nothing but energy. But that's not what happened. Instead, for every billion particles of antimatter, there were 1,000,000,001 particles of matter. That tiny excess is what makes up everything we see today. So, what could have caused this imbalance? One leading theory involves a process called baryogenesis, which suggests that certain conditions in the early universe favored the creation of matter over antimatter. This process might have been driven by hidden forces or interactions that we don't yet fully understand. For example, some physicists propose that the violation of a principle called charge parity symmetry, or CP symmetry, played a key role. CP symmetry suggests that the laws of physics should work the same way for particles and their mirror image antiparticles. However, experiments have shown that this symmetry isn't perfectly preserved, which could explain why matter ended up dominating. Another intriguing possibility is that the imbalance is linked to the behavior of neutrinos. As we discussed earlier, neutrinos are incredibly mysterious particles, and their properties might hold clues to this cosmic puzzle. Some theories suggest that neutrinos and their antimatter counterparts, antineutrinos, behave differently in subtle ways, which could have tipped the scales in favor of matter during the universe's early moments. There's also the idea that hidden forces or particles, such as those predicted by supersymmetry, might have played a role. Supersymmetry is a theoretical framework that proposes a partner particle for every known particle in the Standard Model. If these particles exist, they could have influenced the balance between matter and antimatter in ways we're only beginning to explore. The Baryon asymmetry problem isn't just a curiosity, it's a question that strikes at the very foundation of our existence. Without this imbalance, the universe as we know it wouldn't exist. By unraveling this mystery, scientists hope to uncover new insights into the hidden forces and processes that shape the cosmos. As we continue our journey, we'll dive into another fascinating concept, the Unruh effect, which explores how an accelerating observer might perceive the universe in unexpected ways. Stay with us as we uncover more about the hidden forces that shape our reality. Now, let's turn our attention to a concept that bends our understanding of reality itself, the Unruh effect. Imagine you're in a spaceship accelerating through the vacuum of space. To you, the universe might seem empty and cold, but according to the Unruh effect, that's not the whole story. An accelerating observer, like someone in that spaceship, would actually perceive a thermal bath of particles, a kind of heat radiation, where none seemed to exist before. This bizarre phenomenon challenges our intuition about the nature of empty space and hints at the profound interplay between motion, perception, and the hidden forces of the universe. The Unruh effect arises from the principles of quantum field theory, which describes how particles and fields interact. In a vacuum, space isn't truly empty, it's teeming with quantum fluctuations, tiny ripples of energy that pop in and out of existence. For an observer at rest or moving at a constant speed, these fluctuations remain invisible. But when you accelerate, your perspective shifts. The vacuum appears to heat up, and what was once a calm, empty space now feels like a warm sea of particles. This effect is named after physicist William Unruh, who first proposed it in the 1970s. What makes the Unruh effect so fascinating is its connection to hidden forces and the fabric of reality itself. It suggests that our perception of the universe depends on how we're moving through it. For example, an astronaut accelerating through space would detect this thermal radiation, while someone floating nearby at a constant speed would see nothing. This raises profound questions about the nature of reality. Is the universe fundamentally the same for all observers, or does it change depending on how we experience it? The Unruh effect also has deep ties to other mysterious phenomena like Hawking radiation, which predicts that black holes emit radiation due to quantum effects near their event horizons. Both effects highlight how acceleration and gravity can create particles from what seems like nothing, blurring the line between empty space and a bustling quantum world. This connection hints at hidden forces or underlying principles that govern the behavior of particles and fields in extreme conditions. While the Unruh effect hasn't been directly observed yet, it requires incredibly high accelerations to detect. It remains a cornerstone of theoretical physics. It challenges us to rethink our assumptions about space, time, and the nature of reality. Could this effect reveal deeper truths about the hidden forces shaping the universe? Or does it point to a more profound connection between motion, energy, and the quantum realm? These are questions that continue to drive research and spark curiosity among scientists. As we move forward, we'll explore another captivating theory, the cyclic universe, which suggests that the cosmos undergoes endless cycles of expansion and contraction. What hidden forces might drive this eternal dance? Stay with us as we uncover more about the mysteries that shape our universe. Now, let's journey into a theory that reimagines the very fabric of time and space, the cyclic universe. Picture the cosmos not as a one-time event, but as an eternal dance of expansion and contraction, a never-ending cycle of birth, death, and rebirth. This idea challenges the traditional view of the Big Bang as a singular beginning, proposing instead that the universe has no true start or end. Instead, it pulses like a cosmic heartbeat, driven by forces we are only beginning to understand. At the heart of the cyclic universe theory lies the concept of hidden forces that govern these cycles. One key player is dark energy, the mysterious force accelerating the universe's expansion. In this model, dark energy doesn't just push galaxies apart, it also plays a role in triggering the contraction phase. As the universe expands, dark energy's influence grows, eventually causing space to collapse back in on itself. This contraction could lead to a big crunch, where all matter and energy are compressed into an incredibly dense state, setting the stage for a new Big Bang and the birth of a fresh universe. But what drives this cycle? Some theories suggest that hidden forces like quantum fluctuations or exotic forms of matter could be at work. These forces might create the conditions needed for the universe to rebound after a contraction, sparking a new cycle of expansion. Another intriguing possibility is that the laws of physics themselves evolve over time, subtly shifting to allow these cycles to repeat endlessly. This idea blurs the line between the known and the unknown, hinting at a deeper layer of reality that we have yet to uncover. The cyclic universe theory also offers a potential solution to some of cosmology's biggest puzzles. For instance, it could explain why the universe appears so finely tuned for life. If the cosmos has gone through countless cycles, each one refining the conditions for stars, galaxies, and planets, it's possible that the universe we see today is the result of an endless process of trial and error. This perspective shifts our understanding of time from a linear progression to an infinite loop, where every cycle builds on the one before it. While the cyclic universe remains a theoretical framework, it sparks profound questions about the nature of existence. Could hidden forces be orchestrating this cosmic rhythm? And if so, what might they reveal about the ultimate fate of the universe? These questions remind us that the cosmos is far more dynamic and mysterious than we often imagine. As we wrap up our exploration of the universe's hidden forces, we're left with a sense of awe at the vastness of the unknown. From dark matter and dark energy to quantum entanglement and the cyclic universe, each theory offers a glimpse into the forces that shape our reality. But the journey doesn't end here. Science continues to push the boundaries of what we know, inviting us to keep exploring, questioning, and marveling at the wonders of the cosmos. As we bring our exploration of the universe's hidden forces to a close, It's clear that these theories are more than just ideas, they're windows into the profound mysteries that shape our reality. From the invisible grip of dark matter holding galaxies together to the enigmatic push of dark energy driving the cosmos apart, each theory challenges us to rethink what we know about space, time, and existence itself. Quantum entanglement reminds us that the universe is deeply interconnected, while the multiverse theory opens the door to infinite possibilities. String theory and the holographic principle stretch our imagination, suggesting that reality might be far stranger than we ever imagined. The Big Bang and cosmic inflation reveal the explosive beginnings of our universe, while the Higgs field gives us a glimpse into the origins of mass. The Great Attractor pulls us toward cosmic mysteries, and the Fermi paradox leaves us wondering about the silence of the stars. From the simulation hypothesis to the Casimir effect, each theory invites us to question the nature of reality and our place within it. The quest for a theory of everything, the black hole information paradox, and the cosmic microwave background all point to a universe brimming with unanswered questions. And as we've seen, even the arrow of time and the cyclic universe challenge our understanding of beginnings and endings. Together, these 30 theories paint a picture of a cosmos that is vast, dynamic, and endlessly fascinating. They remind us that science is not just about finding answers, it's about asking better questions. Each discovery, each theory, brings us closer to understanding the hidden forces that govern the universe, yet they also reveal how much we still have to learn. So, what do you think? Do these theories spark your curiosity about the cosmos? Which one resonates with you the most? Let us know in the comments below. Your thoughts and ideas are part of this ongoing journey of discovery. And if you're as captivated by these mysteries as we are, don't forget to like, subscribe, and hit the notification bell so you never miss an exploration into the wonders of the universe. The cosmos is full of secrets waiting to be uncovered, and together we can keep exploring the infinite possibilities that lie beyond the stars.